Dear students, welcome to this next lecture of Theory of Generalized Functions MSc Final course. Um, we were studying gamma function. In the last turn, uh, I was discussing with you Euler's product formula for gamma function. I will continue with that. I just started that, and there was some network issue also there. So I'm starting that portion again. We know that the Euler constant is the limit of the convergent sequence 1 plus 1 over 2 plus 1 over 3 and so on 1 over n minus log n. So basically this is the nth term. This is the nth term of the sequence of which the limit is gamma, means the Euler constant. Now, as a generalization of this, I recommend you to see some research papers. You can also see there. You can see this paper of 1993, or one more option you have. You can see level 2003, page number 75 to 78. So just refer to these research papers, research articles, and you will find that the gamma function, the Euler constant gamma, which is actually limit of this sequence, as a generalization of this, actually the same Euler constant gamma is limit of the sequence 1 plus 1 over 2 plus 1 over 3 plus 1 over n. It is all same. The only difference is that now we have not log n here, but we have log n plus alpha, where alpha can be anything which is greater than minus n. Okay, so here now basically this sequence is depending upon the choice of alpha, but for any value of alpha like this, for any value of alpha, such alpha, the limit of this sequence, and moreover the sequence is going to be convergent, and the limit of this sequence will be the same for every alpha. For example, if you take alpha as 0, or suppose I denote it as gamma n alpha. Okay, so suppose we denote it as gamma n alpha, then what do I mean to say is that gamma is nothing but limit of this sequence for every alpha, such in this way. So here you can easily take alpha as 0. Okay, if you take alpha as 0, what you are going to get? If you take alpha as 0, you will get this one, the expression which we have already seen, that expression that we have already discussed about this Euler constant. The same sequence we will be getting for alpha equals 0. So basically, what is the difference between these sequences, or if it still converges, then what is the difference? The only difference that I want to mention here is that the rate of convergence of gamma and alpha depends upon alpha. It means that here, if you take suppose gamma n 0, so gamma n 0 is nothing but the already known definition that we have already seen of this Euler constant. If you can take gamma n 1 over 2, gamma n half, you can take gamma n 1, right? So the rate of convergence of these sequences will depend upon alpha, and there is no more change or no more difference between gamma and alpha and what we have seen earlier. Okay, here what is the meaning of rate of convergence? Rate of convergence, you can easily say that suppose you want to reach there at this point, okay, and you are starting at this location or at this point. So the rate of convergence, you can say that you are going along this path, or you can going along this path, or you can going along this path, or you have to or something saturates, then the increase at which it is saturating. Okay, so that will be the basically the rate of convergence. So the rate of convergence depends upon alpha here, right? We can also say that mention here that as alpha increases, the rate of convergence also increases. The rate increases. Okay, but the important thing, जो सबसे भी important बात है जो आप लोगों को यहाँ से लेनी है, वो ये है कि जो ये आयलर कांस्टेंट आप ले रहे हैं, जो कि ऑलरेडी आप पढ़ चुके हैं, देख चुके हैं, जो कि इस सीक्वेंस की लिमिट होता है, वहां पर आप अगर n न लेकर के log n न लेकर, if you are taking log n plus alpha, then still it is okay, but you have to take alpha, but alpha should be such that alpha should always be greater than minus of n. Okay, so you can easily take alpha as 0, 1 by 2, you can take alpha as 1 also, right? If you take alpha as 1, what would you get? We will get gamma equals limit n tend to infinity 1 plus 1 over 2 plus 1 over 3 plus and so on 1 over n, and this time we will get log n plus alpha, and alpha I have taken 1, right? So we will get log n plus 1. So I can directly state this now. Okay, so now we move forward to the Euler product expression or formula for gamma function, right? For gamma function. So we can easily write it as this gamma, or simply you can write log n plus 1 as log of 2 over 1, 3 over 2, 4 over 3, ultimately n plus 1 over n, right? If you multiply these all, you will directly get log of n plus 1 here. Now what I do here is I'm going to write in it as sigma notation, sigma summation notation, m equals 1 to n, and the general term is log of m plus 1 over m, right? So if I use it here for log of n plus 1, I will get gamma as limit n tends to infinity, and then I can also write it as with that sigma notation, right? So I'm going to write it as 1 over m, because if I take summation m equals 1 to n, I will get 1 plus 1 over 2 plus 1 over n, right? And in place of log m plus 1, if I write this, then simply it becomes 1 over m minus log m plus 1 over m. Okay, so if we take as exponential e to the power minus gamma z, because this term is there in the Weierstrass definition of gamma function. Okay, we have seen this term. So if we want to find e to the power minus gamma z for using it further, we can write it as limit n tend to infinity, and we know that e to the power a plus b plus c, or you can say anything like that. If there is a series, there is a summation in the power of e, it will become e to the power a multiplied by e to the power b. So basically this sigma notation becomes multiplication notation e to the power a. So here multiplication means a, b, c, the multiplication runs over a, b, c. So e to the power a multiplied by e to the power b multiplied by e to the power c. So in power of e, if you are having sigma notation, you can simply write it as multiplication term. Now, since there is going to be e to the power something like a sigma notation, so in the same way, you will be able to write it as this sigma notation will become multiplication notation, m equals 1 to n, and what you will get, since you are multiplying this gamma with minus z, so e to the power minus z over m, and we also get e to the power, actually this minus becomes plus, so we get e to the power z times log m plus 1 upon m, and log and n log m is log m to the power n. So basically I'm going to write it as, directly I'm going to write it as log m plus 1 divided by m to the power this z. Z comes here. Okay, so it is same thing. Now e to the power log of something, so this directly becomes limit n tends to infinity m equals 1 to n e to the power minus z over m, right, e to the power minus z over m, and this becomes m plus 1 divided by m to the power z. Okay, so let us call it equation 1, e to the power minus gamma z. Now by Weierstrass definition, what we know by the Weierstrass definition of gamma function, that z of z multiplied by gamma z is e to the power minus gamma z multiplication infinite product, actually m equals 1 to infinity 1 plus z over m to the power minus 1 and e to the z over m. So you can directly write it as e to the power minus gamma z, and yes, as we know sequence of partial sum, the same way we have sequence of partial products here. So we can directly write it as limit n tends to infinity, multiplication m for m equals 1 to n, and the same thing 1 plus z over m to the power minus 1 e to the power z over m. If this limit exists, and this limit must exist if this infinite product exists, and that exists because of this definition of Weierstrass definition, Weierstrass definition of gamma function. So here, since this is convergent, so this limit obviously exists, and here what I am doing it here, that if this limit exists, then it means that we are going to take a sequence of partial products. Okay, as the case of we know in the case of convergent series, in the same way we study convergent infinite products also, and in case of convergent infinite products we must have the sequence of partial products must be convergent. तो यहाँ पर जब आप लिमिट लेंगे sequence of partial products की, तो वो लिमिट एग्जिस्ट करनी चाहिए, वो हम लोग यहाँ पर मानते हुए चल रहे हैं क्योंकि ये Weierstrass डेफिनेशन होल्ड कर रही है. चलिए अब देखते हैं, ये बन जाएगा e to the power, and also what I suggest here, use equation 1. Okay, use this equation 1, and from this equation we get e to the power minus gamma z. So if we directly substitute this value there, we directly write, we can write limit n tends to infinity, and obviously e to the power minus z upon m was there in this for this expression, for expression of this term, and e to the power z by m is also there. So those two terms cancel each other, and ultimately we get this infinite product m equals 1 to n, and 1 plus z over m to the power minus 1. And yes, what the other term was there, other term is m plus 1 upon m to the power z, m plus 1 upon m to the power z, and nothing like that. Okay, so this is z gamma z, right? So this, and this is your the most important result, Euler's product expression for gamma function, and we have proved it with the help of this Weierstrass definition of gamma function. ठीक है, हम लोग अगर इसको चाहें तो इसको अलग अलग करके भी लिख सकते हैं. दिस विल बिकम 1 प्लस 1 अपॉन m टू द पावर z. वो डिफरेंट फॉर्म्स में आप लिख सकते हैं, हालांकि इसकी कोई ज़रूरत नहीं है. दिस इज इनफ. So this is an important result. Now we are going to prove a corollary, and that corollary is also very important. What we are going to prove, let me state it. We are going to prove this gamma z is limit of factorial n to the power z, factorial n into n to the power z, z plus 1, z plus 2, z plus n. Okay, so this is also a very good result. We are going to prove this result now. So we will start from this equation 2, which is Euler's product for gamma function. Now we have seen that gamma z is nothing but 1 over z limit n tends to infinity, and since we can write it as sequence of partial product, so we write in product from, for m is equal to 1 to n, 1 plus 1 upon m to the power z, and 1 plus z upon m to the power minus 1, right? Now gamma z, from here you can write it as m plus 1 over m to the power z, and this you can write as m divided by m plus z. Okay, m divided by m plus z. Now if you just open this product for m is equal to 1 to n, what you are going to get? You are going to get 1 over z limit n tends to infinity, and for m equals 1, this will give you 2 upon 1. For m equals 2, this will give you 3 divided by 2, and the last term for m equals n, you are going to get n plus 1 upon n to the whole power z, and here you will get 1 multiplied by 2 multiplied by 3 dot 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 multiplied by n, and in the denominator you will get 1 plus z, 2 plus z, and so on, n plus z. Okay, so this is gamma function, gamma z. Now we can write it as limit n tends to infinity. Take this z inside, and this what is this? This is factorial n. So factorial n, all these terms are get cancelled, so you just get n plus 1 to the z. Okay, n plus 1 to the z, this remains there only this term remains, factorial n, and in the denominator we get, you take z inside, z 1 plus z 2 plus z, and the last term is n plus z. Okay, so if the limit exists, we know that limit of xn sequence xn will be same as limit of sequence xn plus 1 or xn minus 1. okay, xn plus 2, everything, ये सभी सब सीक्वेंसेस की लिमिट सेम होगी. सो यहाँ पर हम लोग अगर हम लोग n के प्लेस पर n माइनस 1 सब्स्टिट्यूट कर दें पूरे में, तो कोई उससे कोई फर्क यहाँ पर नहीं पड़ता है. सो वी कैन राइट इट एज gamma z equals limit n tends to infinity, and now it becomes factorial of n minus 1, and that was, I think, n plus 1 to the power z. That will become n to the z divided by z 1 plus z, and now the last term was initially n plus z. Now the last term is n minus 1 plus z. Okay, now you just multiply the numerator and denominator both with n times z plus n. Okay, you add this, you multiply this term to this factorial n minus 1, and what you are going to get, you are going to get factorial n, right? And also this is, let it be n to the power z, and do one thing, that multiply this term to this, so you get z 1 plus z 2 plus z and so on, n plus z, right? n plus z. और जो टर्म बच गया वो क्या है, वो है z plus n upon n. Okay, if you take limit n tend to infinity here, n tend to infinity, you just divide by n, you are going to get 1 plus z over n upon 1. So you will just get 1. So this converges to 1. So you simply get this term only. Okay, you simply get this term only, and this is for gamma z. You must try this. Okay, so first is gamma z plus 1 equals z gamma z, and it is analogous to that you have seen in your BSc part 1, that gamma of p plus 1 is p gamma p. Do you remember that? Gamma of p plus 1 is p gamma p. So here, but that time p was a real number, but here z is a complex number. So this is the main difference. So you will need Weierstrass definition, or you will need Euler's product formula for gamma function, or you may need this corollary also, right? तो इन सब में से आप ये corollary use करके भी आप कर सकते हैं. So you have to prove this with the help of what you have learned in this last week, Weierstrass function or Euler product, etc., etc. So this is your first homework. The second homework is that you have to prove that gamma 1 is nothing but 1. And the third thing, ये तो मैं आपको ऑलरेडी दे चुका हूँ कि गामा डैश डेरिवेटिव जो हम लोग डिटरमाइन करते हैं, गामा डैश हाफ अपॉन गामा हाफ, और ये किसके इक्वल होता है, माइनस ऑफ गामा, दिस इज आयलर्स कांस्टेंट, माइनस गामा माइनस ऑफ लॉग ऑफ 2. सो ये आपका पुराना होमवर्क है और ये आपका नया होमवर्क है. यहाँ पे ये आपको करना है. दिस इज मस्ट टू बी डन. वन मोर थिंग, जो मैंने आप लोगों को फ्रोबेनियस मेथड बताया था, ठीक है, अब मैं उम्मीद कर रहा हूँ कि फ्रोबेनियस मेथड भी आपने देख लिया है, और आप लोगों के पास में मैं आपको 3 दिन का टाइम और भी दे दे रहा हूँ, संडे तक का टाइम और दे रहा हूँ, ताकि आप लोग जो लेजेंडर पॉलिनोमियल में आप लोगों ने बेसिक पार्ट 2 में पढ़ा था, स्टार्टिंग फ्रॉम इट्स सीरीज सॉल्यूशन, जो कि मैंने डिस्कस भी कर लिया है, लेकिन फिर भी स्टार्टिंग फ्रॉम इट्स सीरीज सॉल्यूशन, देन फॉलोड बाय recurrence relations and many more things are there, generating function of Legendre polynomial, वो सारी चीजें आप लोग उसको कंप्लीट करके रखेंगे. ठीक. Now we move forward to the next heading, and the next heading is of factorial notations. or you can also write it as factorial function. Name, you are already introduced to this term factorial, but here let us see what is it. If alpha is not equal to 0, then we define factorial notation of alpha for 0, alpha 0 as 1, and if n is greater than or equal to 1, in that case, if n is a natural number, you can say, then we define alpha, alpha plus 1, alpha plus 2, and so on, alpha plus n minus 1. So this is factorial function. Alpha n, this is for n being a natural number, and this is for alpha 0. But alpha should must not be equal to 0. So now why we call it factorial, why we use factorial term here? So very simple explanation to this. If you just put alpha equals 1, what do you get? You will get 1 0 as 1, and for 1 n you will get 1 multiplied by 2 multiplied by 3, and the last term you will get directly, you will get n. So this is nothing but this is factorial n. So since we are getting factorial n here, and we are getting factorial 0 here, because factorial 0 is nothing but it is 1. So you can say that factorial that you already have learned, that is special case, that is a special case of this factorial function, and that special case is for alpha equals 1 here. Okay, so now we let us move forward to our next some results we will see now. The first result is that alpha is obviously not equal to 0, keep in mind. So the first result is alpha 2n, and it is equal to 2 to the power 2n. Alpha divided by 2 is factorial notation, and then alpha plus 1 divided by 2 factorial n. It is very easy to prove it. What is basically alpha 2n? Alpha 2n is nothing but alpha plus 1, alpha plus 2, alpha plus 3, alpha plus 4, and so on. The last two terms, let me mention. The last term will be alpha plus 2n minus 1, right? And the second last term will be alpha plus 2n minus 2. Okay. Now what I'm going to do is that I'm going to make two groups of these terms, and first of all, let me divide all these brackets or terms by 2 each. So divided by 2 divided by 2 divided by 2. How many terms are there? How many products are there? It is very easy to answer. In every factorial notation, if you are taking factorial 2n, so there will be 2n brackets there, or 2n terms there. So how many 2's will be there? So there will be 2 to the power 2n, that will be multiplied and that will be divided, and if you will be dividing, you will get alpha divided by 2, and this is from here, and from this I'm skipping alternate terms. If you divide by 2, you will get alpha divided by 2 plus 1. Then from this term you will get alpha divided by 2 plus 2, and yes, from this term you will get from this term actually you will get alpha divided by 2 plus n minus 1. Okay, now the remaining terms, now I'm going to write the remaining terms. So what are the remaining terms that I skipped? The remaining terms are this one, alpha plus 1 divided by 2, then this is alpha plus 3, and I can write alpha plus 3 as alpha plus 1 plus 2, and since I'm dividing it by 2, so I can directly write it as alpha plus 1 divided by 2 plus 1. Okay, now the next term will be alpha plus 1 divided by 2 plus 2, and similarly the last term corresponds to this, and if you just add 1 here, then you have to subtract 1 also, so you will get alpha plus 1 divided by 2, and this will be 2n minus 2 divided by 2, so you will directly get n minus 1. Okay, now so this is very easy to see that this is 2 to the power 2n, and what is it? Suppose alpha by 2 is p. Suppose alpha by 2 is p. So you are getting p plus 1, p plus 2, p plus, and so on. P plus n minus 1 is the last term. So this is nothing but pn. Factorial notation you are getting here. How many brackets are there? There are n brackets. So this is nothing but alpha by 2 notation n, factorial notation n. And this second group of terms gives you alpha plus 1 over 2 factorial notation n. So this was a very easy, straightforward result. Similarly, you can try yourself. Alpha 3n, what will you get? You will get 3 to the power 3n, and this time इस बार हम क्या करेंगे कि हम लोग 3 ग्रुप्स बनाएंगे टर्म्स के. जो पहला ग्रुप होगा वो अल्फा से शुरू होने वाले टर्म्स होंगे, जो दूसरा ग्रुप होगा वो अल्फा प्लस 1 से शुरू होने वाले टर्म्स होंगे, और जो तीसरा ग्रुप होगा वो अल्फा प्लस 2 से शुरू होने वाले टर्म्स होंगे. So directly you will get, and total how many brackets are there? 3n, and you are going to partition those 3n brackets into 3 groups of n brackets each. तो 3 फैक्टोरियल नोटेशन तैयार हो जाएंगे, और पहला फैक्टोरियल नोटेशन होगा अल्फा बाई 3, क्योंकि आप 3 to the power 3n आप 3 सबके डिनोमिनेटर में ले रहे हो. So you will get alpha plus 1 divided by 3 factorial notation n, and alpha plus 2 divided by 3 factorial notation n, right? If you directly generalize it, then you can write, for k being a natural number, you can directly write alpha kn, okay? So, in the previous result that we proved, k was 2. In this one that I'm giving to you to try, k is 3 here. Okay, so in general, for k being any natural number, you can directly prove that you will get, what did you get? What did you got in the previous? Here you got 2 to the power 2n, and now you're getting 3 to the power 3n. So you will in general get k to the power kn, and since there are total kn brackets, so here you will get n brackets, m brackets, m brackets, m brackets, k times. Okay, n multiplied by k is again kn. So you can directly write it as alpha by k n, alpha plus 1 n, alpha plus 2 n, and so on. The last factorial notation you will get alpha plus k minus 1 k n, right? फैक्टोरियल ये जो आपका सिग्मा नोटेशन है, उसी तरह से पाई नोटेशन या मल्टीप्लिकेशन नोटेशन में भी आप इसको एक्सप्रेस कर सकते हो. क्या करोगे आप? इसको लिखोगे i इक्वल्स 1 to k अल्फा प्लस i माइनस 1 डिवाइडेड बाय k factorial notation, क्योंकि if you open this multiplication, the first term will be alpha by k, right? The second, for I equals 2, you will get alpha plus 1 divided by k factorial notation n. Okay, so in this way you can prove it also. Now next important result that I am going to explain is, if alpha is neither 0 and alpha is neither equal to any negative integer, so if alpha is neither 0 nor any negative integer, then factorial notation n of alpha is equal to gamma of alpha plus n divided by gamma of alpha. ओके तो कैसे इसको प्रूव करेंगे, बहुत आसान सा रिजल्ट है. You have already proved that gamma alpha plus 1 or gamma z plus 1 is z gamma z. Okay, you have done it. I have given you as an assignment today using ILS product or Weierstrass definition of gamma function. So if you just replace it by alpha here, you can take alpha any complex number, okay, complex number. So but that real part of alpha should be greater than 0, because no, you know the condition, real part of alpha should be greater than 0 for being this this to be defined. Okay, gamma of alpha plus 1 you will get as alpha gamma alpha. From here you get this, right? Now so gamma of alpha plus 2 you can write it as alpha plus 1 gamma of alpha plus 1. Okay, and then gamma of alpha plus 1 you will get alpha plus 1 gamma alpha, right? The same way, if you write gamma of alpha plus 3 you will get alpha plus 1. You simply write it as alpha. This is factorial notation. Alpha से शुरू होकर और दो brackets आप ले रहे हैं consecutive brackets, so this is factorial 2, and here you get gamma alpha, right? This is nothing but this is factorial 1. So here you can, okay, let me write it. You will get this. So this is nothing but factorial notation again. So gamma of alpha plus n, what would you get? You will simply get alpha factorial notation n gamma alpha. Okay, and from here you have got this result, this one, that alpha factorial notation is gamma alpha plus n divided by gamma alpha. Let us have a look at another very important result. That important result is that limit of n tending to infinity of factorial n minus 1 n to the z divided by gamma of n plus z is always going to be 1. This is most important result, and that will not only we will use in this chapter, but throughout this course of theory of generalized functions, this result is going to be again and again recalled, again and again used. So how do you prove this? How would you prove this? We have already seen that from the corollary, of that ILS product formula for gamma z that we proved today in this video itself, that gamma of z is limit n tend to infinity. Okay, we have seen this result today. It is factorial of n minus 1 n to the z divided by z plus 1 z plus 2, and what was the last term? The last term was, I think, z plus n or z plus n minus 1. Let me see that. I think let me see that. Yes, it is the result. So gamma z is limit n tend to infinity factorial n n to the z plus 1 z plus 2 and so on up to z plus n, or you can use this also here. This, if you use this one from this only, I mean to say that you don't multiply with this n into z plus n upon n into z plus n in both numerator and denominator. You can use this gamma z, limit of this as gamma z. Okay, so I'm just using this here. Yes, same thing. So this is actually limit n tend to infinity, and this factorial of n minus 1 multiplied by n to the z, sorry, it's multiplication, n to the z, and what is it? It is nothing but factorial notation, right? Now if what you do here, if you just divide by gamma z both sides, you will get this here. Okay, z factorial n multiplied by gamma z. And we just proved in the previous slide that alpha factorial n gamma alpha is nothing but gamma of alpha plus n. So if you can directly use it there, because alpha is any complex number here. So here if you write z factorial n gamma z, you will get gamma of z plus n. So directly you can replace this. You can just replace this with gamma of z plus n, and you get this result. So this is a very important result, factorial n minus 1 n to the z divided by gamma of n plus z or z plus n, and the limit is always going to be 1. This is most important, always keep in mind. Okay, thank you.